Everybody, there's going to be a visual demo today, so if you're seated way in the back and you can't see the dice, I recommend coming forward so that you can see the dice. Okay? So today we're going to cover what is generally considered the classical material of any algorithms course. If your algorithms course does not cover this material, then it's not an algorithms course. We're going to talk about elementary sorting operations. All right? This is going to be a little bit different from our usual fare of talking about classes and, object-oriented structures in general. Today we're just going to be talking about the algorithm itself. We're going to sort of hold constant the data structure as just an array. So, pardon me. So good. An early computer, Charles Babbage's analytical engine of the 1830s. Just to set the stage. So, in the early days of computing, conventional wisdom stated that around 30% of all computing cycles were spent sorting things. This is, actually one of the great advantages. Like, to some extent, early computers were early sorting machines that you could, sort through large amounts of data quickly with. It's unlikely, I would say, that if you took all of the computing cycles that are occurring everywhere in the world right now, 30% of them are still spent sorting things. But this is likely because people have realized the value of keeping things sorted, not because sorting itself has become less valuable as an operation. Anytime that you see any data arranged by date, magnitude, or any other means of comparison, a sort has most likely either been performed or the data has been kept in a sorted fashion. Over the next few lectures, we'll be discussing elementary sorts, the simplest sorting algorithms. These are also sometimes called in-place sorting algorithms. Because if you're clever with indices, you don't actually require the declaration of any additional memory space beyond that which the array is stored in. That means that these elementary sorting algorithms are still very much used in memory constrictive environments. Does anybody have an idea what a memory constricted environment might look like? Some place where you wouldn't have a lot of memory available? Yes?
Like a microcontroller?
Microcontrollers, yes. So if you're designing what are called embedded systems, right, which are computers which are embedded in electronic devices, a car, the modern automobile, has over 100 processing cores in it now. Each one of those is what we call an embedded system, right? Because these are production electronics, every piece of memory that you put into a electronic device costs money, right? It comes at the expense of the bottom line. It either eats into the profit, or you have to charge more for the electronic, which means the electronics, which means you can't perhaps outcompete your competitors as well. So, in embedded systems, it is not only very common not only to program in C as your main language, but even to program in assembly, because it's so much more compact than C. You often are sort of fighting for your boss for every byte of memory that you want to allocate to your system. If you think about production runs of like tens to hundreds of millions of devices, even saving, 0.002 cents on a device pays your salary for the year, So in these types of situations, low memory sorting algorithms are precisely and exactly what you need. And it turns out that elementary sorts actually do very well. Although once we get through the elementary sorts, we'll be talking about some advanced sorting algorithms, including merge sort and quick sort, if you've heard of them. I'll just say it again because I notice a few more people have snuck into the back since I said it the first time. I'm going to be doing an actual physical demonstration today, so if you can't see the dice from where you're sitting, I recommend moving forward so that you can. Okay? That, you know, my eyes are terrible. Maybe your eyes are a lot better than mine. I tried to get as big. I tried to make the dice as big as possible. I expected them to be like this big, but that's how big they come from Amazon. Man, like impossible to judge sizes on that bloody website. So, notable sorting algorithms. Sorting algorithms have been a topic of research since the inception of algorithms as a science. To some extent, sorting algorithms were the birthplace of algorithms research. There are a large number of sorting algorithms in existence. This is just a selection of some of the more popular ones. The ones that are highlighted in colors are the ones that we'll be studying in this class. So, in this, the elementary sorts that we're going to be studying are selection sort, insertion sort, and shell sort. We will then, of course, study merge sort and quick sort, and then we have some slides on priority queues. In addition, we have heap sort, bubble sort, library sort, and Tim sort. Tim sort was written specifically for Python, and it's the sorting algorithm used by Python, which may be of interest to you. Library sort is kind of an interesting one. It's the way that it works roughly is it leaves gaps in the array so that you can speed up the insertion of values at the ends of sort of bookshelves. Like the reason it's called library sort is like if you go to the library, each shelf will have some space on the end, like normally, unless it's like deep in the basement of Thode. And you know, you can insert books without having to move books to different shelves. That's kind of the idea that behind library sort. But if you want a full list of them, as well as comparisons of their runtime and performance characteristics, the Wikipedia page is extremely informative. They've even highlighted which ones are good and which ones are bad. You'll notice that selection sort is bad, except for memory. So yeah, at any rate, it's a lot. Question?
What if they need a memory of 1?
It means it doesn't, it requires only the amount of memory that you have to allocate, aside from that which is allocated to the input itself, is constant.
Oh, so it's just like constant storage?
Yeah, as we're going to see with selection sort, you only need to define one swap variable.
Yeah.
And that's it. So that's constant. No matter how big the array is, you only need one variable for swap space. Make sense? Good. Any other questions? Good. So, this is kind of the definition of an elementary definition. But before we talk about how we go about sorting a data structure, it would be good to have a definition of what does it mean for something to be sorted, right? So the process of sorting is rearranging a sequence of objects so as to put them in some logical order. Most of the time, we're going to be doing this for numerical value, right? Sorting by integers. However, it doesn't necessarily have to be integers with, the less than, greater than comparison. If you think about Python and the way that it does classes, for any class you can provide a definition for comparison operators, greater than, less than, greater than equals, less than equals. It doesn't necessarily matter what that's even doing, what your means of comparison is, so long as you have a definition for these comparison operations then sort is meaningful over the data. Does that make sense? So, for example, in Haskell, the thing that you would say is that any sortable class, or any sortable data type, has as a supertype orderable, right? But you know, supertypes, subtypes, probably not something, if you guys probably haven't gotten that deep into type theory yet, I would imagine. Yeah, it's like, you know, any data type which can be ordered is a member of orderable. And it's like, well, wouldn't that be all of them? And it's like, well, actually, no. Because what does ordering mean over Booleans? Right? It doesn't, there's no intuitive sense of like true being greater than false. That doesn't really, like that's not something that makes sense in terms of Booleans, right? Just even if in C you totally can order them because they're all integers under the hood, but you know, anyway. We will be concerned with sorting arrays primarily because we are completely addicted to that sweet, sweet constant lookup time. In general, it doesn't matter if you're sorting into ascending or descending order. The only thing that changes is the nature of the comparator. So you can swap, you know, less than equals for greater than equals, and the algorithm will remain exactly the same. You only have to like modify 2 characters in the actual algorithm. For ascending order, the following property holds after sorting. If n is less than m, then array at n is less than or equal to array at m. Make sense? So far, so good? Hopefully, hopefully nobody's asleep yet. So, let us discuss our first sorting algorithm, selection sort. Selection sort is, I don't know if it's the simplest possible sorting algorithm. I'd say the simplest possible sorting algorithm is one that fails and just does nothing. But you know, whether that's a good algorithm is another matter. So it's in the same category of bubble sort, if you know what bubble sort is. How many people have heard of selection sort? How many people have not? All right, so it's fortunately very easy. So, selection sort proceeds by building up a sorted section of the array. It traces through the unsorted section at each iteration, finds the minimum value inside of that unsorted section, and adds that to the sorted section via a swap operation. We repeat this process of swapping the minimum to the end of the sorted section until we have processed the entire array. All right? So this is how it works. All right? I don't have a single one in there. All right. So you decide that this guy is the sorted section, right? You then trace through looking for the minimum value. You decide that it's this 3. Swap. That becomes sorted. You then trace through looking for the minimum value. Here it is. There you go. Sort of get the idea. Trace through minimum value. Well, you can just put it there. Don't have to swap it. Like that. There we go, there we go. There we go. And there we go. Selection sort. All right. You don't have to clap. Clap when you see shell sort, because that one's fun.
Okay.
All right. So, selection sort. Right? Here's an example of it with respect to, you know, letters where, you know, whenever it's letters, it's always in lexicographic order. Yeah, you just go through the unsorted section, selecting the minimum, popping it onto the sorted section, right? So, the algorithm itself, of course, you'll notice that what we have to do with this algorithm is we have to trace through the entirety of the unsorted section in order to find the minimum, right? To find the minimum requires tracing through every individual element. So, that operation is, in terms of complexity, well, overall it's n squared, but the tracing through the array to find the minimum is? That's linear, yes. And you have to perform it once for each element in the array. So our complexity is quadratic, yes. And big O n squared. So, selections, question?
Yeah, do we have to ever write like it being like count for every single time that like you go to the next one, you technically subtract one from the inner loop? Do we have to ever like specify that or no?
You mean like if you were doing this for an assignment question?
No, just like out of curiosity, just like legit writing it. Because like this might come up for like a midterm, for example. I'm actually confused about this.
So in general, the fact that like you're at this point sorting, 7 items and that's less than n, right?
Yeah.
That's going to be lost inside of the constant, right?
Oh, okay.
So
Okay, so basically constant, so it doesn't really matter.
right. So the geometric analogy is the best one, I think. So if this is n squared, right? We're going one less each iteration of the loop, right? So in actual fact, we have n squared over 2 as being the number of iterations we're actually going through, right? Now, n squared over 2 is, of course, still proportional to n squared, just multiplied by some constant.
Yeah.
So, when we go to big O notation, both of these are big O n squared, because the half is going to get dropped, right? And this is kind of like, this is also the same reason why we generally don't care about how many times an if statement is executed inside of a loop and stuff like that. Right? Make sense?
Okay, yeah. I'm looking at it way too back.
Yeah. So, complexity is big O, or big theta n squared actually. Running time is insensitive to input. One of the interesting things about selection sort is that its runtime is completely independent of the actual state of the array itself. This is, stability can be a good thing, but as we're going to see with insertion sort, we might be able to take advantage of an array being already partially sorted, right? So, yes, even if only one swap needs to be performed in adjacent numbers, we would still need to run through the entire selection sort algorithm. Incidentally, what's the complexity for checking for sortedness? How long does it take to check to see if an array is sorted? Oh, you didn't have your hand up? No, okay. Anybody? Yeah. Yep, it's linear. So, the tiny advantage, the very smallest advantage here to selection sort is that it performs the minimum number of write operations possible for a sorting algorithm, which, that's possibly useful if your RAM is written on something that it takes a very long time to perform any write operations on, but somehow can be read very quickly, So, if your RAM is something like, chiseling numbers in masonry, then this would be a good sorting algorithm for it. Any questions about selection sort? Yes?
Let's say, for example, we're trying to sort an array, and we have two indexes with the same value. Will the swap still occur?
So generally speaking, no. If two, like, if we have two things which are adjacent, which are the same, there's no reason to swap them. So we don't. Yeah. Yes.
Oh, could you go back to the previous slide with the Java code? I have a question about that. For like the exchange, are we able to use that as, like, say for example, for, like when we're actually exchanging values, or no? The EXCH one.
Yeah, I'm not sure where that's. I don't think that's like an inbuilt Java method or inbuilt Java function. Maybe it is. Does anybody know enough Java to know if that's like a library function? No. Safest thing would be to just do the swap yourself.
Yeah. Oh, it says on the comment, it says see page 245 for last exchange is.
Oh. Alright, so they are defined elsewhere in the text.
So like, I remember you saying like you have to like physically write out a lot of our algorithms, so like we're technically not allowed to use this, or?
Well, see, the thing is, the textbook will have defined it by writing it out, right? So if you want to use it, you have to write it out. It's not a library function,
Yeah.
right? Any other questions? All right. How many of you have heard of insertion sort? Fewer. How many of you have not heard of insertion sort? More. Good. We're getting there. So. Oh wait, yes. This is a good comic. This is like my favorite slides comic, so I'm going to actually read it to you. All right. Cavemen. Who can explain frog sort algorithm? Start with empty list. For each integer, put that number dead flies in one box. Then put frog in each box. When frog leave box, append boxes fly number to list. More fly take longer to eat. When all frogs gone from boxes list order. What is maximum step number? Log frog boxes. Very good. Now homework is program frog sort on home frog pewter. Bah, me understand, but keep getting off by frog error. That's my favorite one, so I thank you for indulging me in that. I don't get a lot of opportunities to use my caveman voice, you know.
Where do you find all these memes?
Where does anybody? It's the internet, man. You live in the information age, you know. So. Selection sort works, but performs many redundant comparisons of examinations. As you may have noticed, a lot of the, finding the minimum takes time, and, it works, but we can do better. Insertion sort minimizes the number of examinations that do not lead to a swapping operation. Insertion sort only makes one pass of the array, sorting as it goes, and the overall algorithm is to examine each element in the array, passing the element back through the sorted section of the array until the correct spot for it is found. So it's like almost the inverse of the previous process. Rather than finding the right number for the next slot, we take the next number and find the right slot by performing additional swap operations. Does that make sense? All right. So. Oh. Muchas gracias. There we go. All right. So, in the same manner of selection sort, we're maintaining a sorted section on one side of the array, right? So, we'll obviously start that off with just one element. We then examine the next element. With respect to this element, these guys are sorted. So we do nothing, all right? We then examine the next one. These two are out of order, so we swap them. Now that's sorted, or I should say, it's not that we just look at all the numbers and say this is sorted. The way that we tell that it's sorted is we examine these two, we examine the next pair. If they are in the correct order, then we can stop, right? So there we go. 2. Swap, 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 end of array, finished, that's sorted. Swap, swap, swap. Sorted, swap, 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 swap. These are sorted because, you know, being equal is also sorted. So, whoop, oh no, oh geez. It was something like this, oh no. Okay, I'll have to be more careful. There we go. Yeah. No, segfault is falling off the table. So, there we go. Comparison, swap, 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 swap. There we go. So you'll notice there are a lot of swaps going on. This is kind of just, you know, par for the course with these types of sorting algorithms. This is something actually that we're going to improve when we get to our next algorithm that we're going to talk about. There we go. And finally, swap, 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 swap. There you go. So, that procedure. For each element of the array, the unsorted element is compared to the largest element in the sorted array, which it will always be adjacent to. So you always know where the beginning of the sorted section is, because it's always just one down from where the one you're examining is, right? If the unsorted element is smaller than the element it has been compared to, those elements are swapped, and the unsorted element is then compared to the next largest element in the sorted section. This proceeds until the unsorted element is greater than or equal to the element it has been compared to. This means that it has been sorted. At this point, the size of the section of the array we consider to be sorted increases by 1, and we examine the next unsorted element. Make sense? Here's another visualization of that. The green section is the sorted section. The blue number is the element that we are currently examining and passing back. Make sense? Any questions? Yes?
So in this algorithm, are we defining two arrays?
No, this is another in-place algorithm. You'll notice, like when I was swapping it here, they didn't leave the rail. I didn't have to put them somewhere else. So these are all in-place swaps. Just like selection sort, we don't have to define any alternative space for storing things. We will once we start getting into things like merge sort, but for our elementary sorts, again, they're very memory conservative. Any other questions? Okay, so here is Insertion Sort, the Java algorithm. So, you know, we have our big loop, which is basically looping through each one of these guys as the thing we are examining. And then we have an inner loop, which is, you know, testing to see if this thing is greater than or less than the thing that it's next to, and then passing back, right? So let's talk complexity. What's worst case scenario? Well, rather than talking about complexity in it initially, what's the worst possible, what's the worst array to sort? Yes?
One that's sorted backwards?
One that's sorted backwards, yes. So if you, okay. you took this, that's the worst case scenario, right? Because each element is as far as possible from its correct point, its correct position, right? What's the best case scenario?
Oh, it's already like sorted, so you just gotta rail it down pretty much?
Exactly. Best case scenario is that one, right? Because the distance each number has to travel to achieve its correct position is 0, right? So, given that insertion sort only really needs to check to see if it's already sorted in the best case, what's the best case time complexity for insertion sort?
Oh,
Yes, linear time. What about the worst case?
squared?
Yes, O(n) squared. Oh, and best case is omega n.
Right.
Yeah. So, any questions? Yes.
Yeah, so for the insertion sort, we always assume that after we sort it, the order is asymptotic, right?
I lost the end of that sentence. Could you speak up, please?
So after we use those sort algorithms, it is always in a ascending order, right? From small to big.
I'm doing it this way. All you would need to do it the other way is change the definition of less, right, to return true if they're in the other orientation, and that turns this from an ascending sort to a descending sort in one step.
And that is also called a insertion sort, right? Since they have basically the same logic.
Yeah, the method used to perform the sort is independent of whether you're sorting ascending or descending. Yeah. It's the same either, like the algorithm is exactly the same either way. All you're changing is like whether you're using greater than equals or less than equals, right?
Yeah.
Any other questions? That's a good question. Okay. So, in selection sort, the number of operations to sort the array is invariant with respect to the size of the sorted section. In insertion sort, the operations it takes to sort each element depend on the degree of disorder in the array. This makes it an adaptive algorithm. Degree of disorder is a measure of how far off the array is from a sorted configuration. A good measure of this is the number of adjacent swaps it would take to order the array. So, if you imagine bubble sort, right? The number of swap operations that are needed to perform bubble sort, that is equal to the degree of disorder, right? Incidentally, because both bubble sort and insertion sort only swap adjacent dice, or numbers, but in this case dice, they both will perform the precise same number of swap operations, though insertion sort does many fewer examinations because it stops when it decides it's in the correct order with respect to the sorted section. Make sense? Question?
I'm just wondering, for best case, do we use omega because it's the lower bound and we're talking about best case? Like, why are
Yes.
we... Okay.
Yep, that's exactly it. Yeah. The actual runtime of the algorithm has linear time as a lower bound, right? It can never be better than that, so that's omega. Any other questions? So, we've kind of already talked about this, but best case is an already sorted array. Complexity is omega n. Requires only linear traversal of the array. The worst case scenario is a fully disordered array, i.e. a reverse sorted array. Each element must be swapped back to the front of the sorted section. Complexity, big O n squared. So, does this algorithm have a big theta defined?
couldn't seem no, because its best case is different from its worst case.
Its best case is different from its worst case, so there's no big theta in this case. Right? So, all right. Shell sort. How many people have heard of shell sort? How many people know how it works? Because having heard of it and knowing how it works are two different things. Yeah. How many people have never heard of shell sort before? All right. So this should be new. So, so insertion sort is an improvement over selection sort, but we can do better. In insertion sort, each swap only fixes one unit of disorder. It is possible to increase our efficiency by performing swaps between array elements which are not adjacent. The question is how to do that, right? Selection sort is one approach to that, where you calculate the maximum amount, like you're basically calculating how far off from its correct position each number is, and then swapping it that much, right? Shell sort takes a different approach. In shell sort, we extract subarrays, sort them, and then put them back. By selecting elements that are positionally distant, we can reduce large amounts of disorder quickly, which insertion sort is bad at dealing with. Shell sort is used in embedded system applications due to its small program size and memory efficiency. Also, algorithmic efficiency. Shell sort is among the best of the elementary sorting operations. When you become a PhD, one of the things they train you in very, very assiduously is to never make any definite claims about anything, because you're probably going to be wrong. That's why I say that shell sort is one of the best elementary sorting operations, and not the best, because who the heck knows? The best elementary sorting algorithm may not have been discovered yet. So the key to shell sort is knowing, oh, by the way, shell sort is named after a dude, not like any reference to like snails, all right? Because it's actually quite fast, despite, a possible connection to snails. So the key to shell sort is knowing how to break the array down into subarrays. Subarrays are formed by taking every h element until the end of the array has been reached. The sequence of h values used varies by implementation, with different sequences being proposed by different researchers. The most recent proposal of h gaps was in 2001, despite the fact that the shell sort algorithm dates from, I think, the 70s? Mid-70s, early 70s, something like that. So, one such sequence is 1, 4, 10, 23, 57, 132, 301, 701. This particular order was experimentally derived, and no known equation has yet been discovered which can predict the next number in the sequence. The worst case performance of this sequence is also currently unknown. Just to hammer it home that these things are an active area of research inside of algorithms as a sub-discipline of computer science. So, what do I mean by h-gaps? If we have an array which has been numbered by index rather than by value, and the blue is really not showing up very well, is it? I apologize for that, but there's nothing I can do about it at the moment. Anyway, so if you take an h-gap of 6, then you take every sixth element of that array, and you collect it up into its own subarray, right? So you end up with 6 subarrays, each composed of 2 elements, because this array is 12 elements in length. Another way of sort of visualizing producing h-gaps, if you take the array, right, and you turn it into a matrix by sort of wrapping it around like the periodic table with, you know, taking a width at the top of whatever the H-gap size is, and then you read it vertically, that will also give you your, that'll give you your subarrays. Make sense? Okay. Another example with H-gap of 4. Because we still have 12 elements, we have 4 subarrays, each containing 3 elements as the result of this H-gap partitioning. But notice, right, the important thing to notice, we're not just taking the first 3 elements and the next 3 elements and the next 3 elements. We are interleaving the elements that we are selecting for the subarrays. That's very important because it means that any disorder which is cured inside of any of these subarrays is multiplied by the size of the H-gap. So every piece of disorder that you solve inside of this, like this with an H-gap of 4, that is the equivalent of 4 insertion sort swaps, right? So that's very, very powerful. Once we have our subarrays established, we perform insertion sort on each one of them, and then put the elements back into the original array. Once all the subarrays have been sorted and replaced for one H value, we say that the array has been H sorted. So after we decompose into, 6, H-gap of 6, we do all of the sorting on all of the subarrays, put everything back into the original array, we call that array 6 sorted. Right? So the entire success of this algorithm hinges on the fact that when you have an array which is, for example, 21 sorted, and then you 7 sort it, it's still 21 sorted. Right? Sorting by smaller gaps does not unsort larger gaps. Right? If that were not the case, then shell sort wouldn't work. As long as the last H value is 1, which is just insertion sort, the array is guaranteed to be sorted at the end, right? Because if you take an H-gap of 1, then you're selecting every single element, which is just insertion sort over the entire array, right? But it's insertion sort after we have reduced the gross amount of H-gaps, right? Or not H-gaps. We've performed all the big swaps, so only small swaps are left, right? So let me see if in the next 6 minutes we can, I can show you shell sort. That's too sorted. Stop that, you. So, just for the sake of interest, the H-gap sequence that I will use for this sort, I will start with 4, then I'll do 2, then I'll do 1. Okay? So, H-gap of 4. 1, 2, 3, 4. 1, 2, 3, 4. We sort this using insertion sort. There we go. Now we put them back. Take the next one. 1, 2, 3, 4. 1, 2, 3, 4. Ah, they're all yellow. Swap. Swap. So you can see that like insertion sort on an array of that size is very fast, right? Put it back, put it back, put it back. Start with this one. 1, 2. Ah, look at that. They're all blue. And swap. Oh wait, no, that's correct. This is the swap. Sorry about that. There you go. Put it back. Woo! That was a 6. That was a 6. There we go. There we go. And now, finally, this one, and this one. It's already sorted, so you put it back. But you can see that this is already, like, way more sorted than we started off with, right? I don't think we even need to do the 2 sort. We could just proceed, well, let's do it anyway. So 2 sort then. Every other element. Right? So, insertion sort. That one's good, 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 that one's good. They're all good. See? Linear time. Linear time examination. Now let's do the other ones. Boink, 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 boink. That's good, that's good, that's not good. There we go. That's good, that's good. So for those last ones, for the 2 sort, we only needed to perform 1 swap, right? Put them back, put them back, put them back. And now, you'll notice that it's, slightly more sorted than it was. The final step is always just insertion sort over the entire array. So, that's good, that's good, that's good. This is not, so we swap. There we go. Good, swap, good, 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 swap, good. Shell sort. You guys get the idea? Is it helpful? Is the dice, helpful?
Yeah.
Okay, cool. Because, the best I can do in diagrams is this, so. But yeah, so yeah, it's like, this is, this algorithm, again, the sequence of H-gaps is critical, right? The H-gap sequence, which is suggested by the textbook, is actually one of the not-so-great ones. It's okay, but it's not the best one. For the Java solution in the textbook, it's just 3h plus 1, so you just multiply it by 3 and add 1, and that's your next value, and they generate those out. Question?
First of all, for H-gaps, do they have to be does every gap have the same number of elements, or can one?
Oh, yeah, no, not at all. If you have, that's a great question. So this is this is like a nice even number that divides evenly by each of the numbers I sorted it by. But if you were doing, for example, an H-gap of 5 on this array, you would get 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Right? Yeah. You'd have this one, you'd have this one, and then you'd have 3 2s. Right? And I realize I just completely disordered my array, but
Do we have to keep track of the best quote-unquote H values or no?
No. You just set it at the beginning of the algorithm to run with specific H values, and then you leave it. It's like you hard code the H values, and you use existing research to tell you what good H values are. You are not expected, when you're writing shell sort, to derive your own custom H values, because it's like friggin' you'd write a paper about it if you did, right?
Wait, did you write your thesis on this?
No, I didn't write my thesis on this. No, it's just a good algorithm, Thank you, everybody.